Standard candles are celestial bodies that form the steps of the cosmic distance ladder, which is a method used to measure the distances to increasingly distant galaxies. Cepheid variables, often known as Cepheids, form the initial step of the ladder. Accurate measurements of the distances to these stars from Earth are essential for establishing exact measurements of objects that are even farther away. The accuracy of Cepheid measurements is crucial for the stability of the cosmic distance ladder, as each step of the ladder relies on the accuracy of the previous one. The cosmic distance ladder, sometimes referred to as the extragalactic distance scale, is a series of techniques used by astronomers to ascertain the distances to celestial objects. Direct distance measurements of celestial objects are feasible only for objects that are within a distance of around 1,000 parsecs from Earth. The methodologies used to ascertain distances to objects that are farther away rely on established correlations between approaches applicable to nearby distances and those applicable to greater distances. Various techniques depend on a standard candle, which is an astronomical entity with a well-established brightness. The latter analogy is used because there is no single approach that can accurately estimate distances across all the ranges encountered in astronomy. Alternatively, one technique can be employed to gauge distances in close proximity, while another can be utilized to estimate distances ranging from nearby to intermediate. Every step of the ladder offers data that can be utilized to calculate the distances at the subsequent, higher step.
Energy of empty space is roughly a gazillion times the energy of everything we see. It indeed is the worst prediction in all of physics, although maybe some of my colleagues here have made worse, I don't know. But what we know is that the energy of empty space cannot be much more than the energy of matter, or we wouldn't be here. And so this problem has been around since before I was a graduate student, but certainly when I was a graduate student, and since then, it became called the cosmological constant problem. Why should the energy of empty space not be 120 orders of magnitude larger than everything we see? And as I alluded to in the panel earlier, we were able to go to sleep at night because we knew the answer, because we're theorists. And we knew the answer had to be exactly 0, because 0 is a beautiful number. More than that, there's a other more relevant physics reason. If the energy of empty space was not going to be bigger than the energy of everything we see, we'd have to cancel this big number to 120 decimal places, leaving a non-zero number in the 121st decimal place. No one knows how to do that. But 0 is a number we know how to get in physics. We have mathematical symmetries of the type Frank talked about and others they're mathematical symmetries that might cancel things exactly. So we all went to bed at night knowing that there was some symmetry of nature that would cancel things exactly, and the answer was 0, and so we didn't have to worry about it. But physics is an empirical science. And as I will argue in a bit, the universe doesn't give a damn what makes us happy. And so what we really want to know is that really the case? And the only way to do it is to observe it. Now, it turns out if you put energy in empty space, as has been alluded to in general relativity, it is remarkably, and that is remarkable. And that means if you look at the expansion of the universe, over time, if the universe is dominated by the energy of empty space, the expansion of the universe will speed up, not slow down. Now, as Alex talked about, in 1998, several groups of astronomers were trying to measure not that the universe was speeding up, but they were trying to measure the rate at which the universe was slowing down, because that's what a sensible universe should do. And to do that, they had to measure very carefully the expansion rate of the universe. And I just want to show, to measure velocity and distance, you have to know the distance of objects, you have to have a standard candle. And it's very difficult to get standard candles, and the type 1a supernovae that he talked about have changed everything. Here's that picture he showed. I love this picture. It's of an exploding star as bright as a galaxy that's about 90 million light years away. And one of the other things I want to do, just to add to what he said, to maybe emphasize this point, is that we can use these things. And here's a nice movie made by one of the two groups that he worked for. This is an exploding star. You can see its brightness over time, and its colors, and it'll keep reproducing over time while I talk about it. The amazing thing is that you can do this, and he alluded to why using statistics, but I want to just emphasize it from a slightly different perspective. If you went out tonight, and it's a clear night, and you held up a hole in your hand about the size of a dime, okay, where you couldn't see any stars, with the largest telescopes in the world of the type he showed, you could see 100,000 galaxies in a region that big. And if you do the calculation, once per 100 years per galaxy, if you can see 100,000 galaxies in a single image like that, you're bound to see a star explode, and people like him apply for telescope time to do just that, and they do it. And it's amazing. It's an important lesson. The universe is big and old, and rare things happen all the time. Another lesson that I think has implications in different contexts, as we'll talk about. Things sometimes just happen, even if they're very strange. Okay. This is to show you how much better you can do now. This is a modern Hubble plot with the Type 1a supernovae. This was, of course, developed after the profound mathematical discovery that on a log-log plot, everything's a straight line. But still, aside from that guide to the eye, we can now use that to measure the Hubble constant to an accuracy of better than maybe 5%, not a factor of 10, as when Hubble got it wrong. And that allowed these groups, as he pointed out, to produce result, and this is actually, there was the cover of Science which is shown, but then afterwards, this is the two groups' data. This is the Hubble plot, this is the distance versus velocity, and the question is what happens to it at very far distances? Does it turn up or turn down? And the way to see what happens is to draw a straight line through that data set and make the whole thing horizontal. So a straight line would be a horizontal line here. And what they and the both groups were looking for was to see how these distant supernovae would follow this curve going down, because that's what a sensible universe should do. And what they discovered, to their amazement, is that the supernovae didn't even lie below the straight line or on the straight line, they lay above the straight line. And there's two explanations of this. One, the data's wrong, which it usually is, but in this case it isn't. And two, empty space has energy, and the universe is accelerating. Now, if just for fun you try and fit the data and ask how much energy would you have to add to empty space, fitting the data, you get exactly what we were missing. If you put 70% of the energy of a flat universe in empty space, everything works. That's another reason why scientists are so quick to accept this result. Not just because it was a convincing result that the universe is expanding. There were lots of things that might have suggested that was wrong. But the universe is flat, only 30% of matter, and this fits exactly. So that is the cockamamie universe we live in. That is a profound result. We live in a universe, a flat universe, in which 70% of the universe is dark energy, this stuff the energy of empty space. Almost 30% of it is dark matter, and a little bit of cosmic pollution. Actually, 1% of it is what we can see. It's true that it was mentioned to be 4%, but most of that isn't even visible. If you look at the universe that we can see, if you take all the stars and galaxies and everything you can see on a beautiful night here in Minnesota and get rid of it and us and everything, the universe would be largely the same. So much for a universe made for us. We are a little bit of cosmic pollution in a universe of dark matter and dark energy. And it's changed everything, and I want to spend the rest of the talk talking about the implications. So let me summarize. The dominant energy in the universe resides in empty space. We don't have the slightest idea why it's there, and I want to remind you, we do not have the slightest idea why it's there. And in deference to my good friend Jim Gates, if anyone comes here and tells you they understand it, they're lying, especially if they're a string theorist. And its existence is tied, we think, to the very nature of space and time and to the origin of our universe, which is why it's so interesting to us. And as Alex alluded to, but I'll describe in a little more detail, it will determine the future of the universe. In fact, the reason I got into cosmology was the wrong reason, because it turns out geometry is irrelevant. It doesn't matter whether we live in an open, closed, or flat universe. The future of the universe is determined not by geometry, but by the energy of empty space.